Okay, so today we're going to be working on section in the Larson textbook 8.4, trig substitution. And I just want to remind you that this is something that you would use as a last resort, as an integral tool to use. I call it integration by desperation. So again, this should be a last resort because it is a little bit challenging. So in trig substitution, what we're going to do is we are going to take a radical and substitute in for that radical a trig function. And actually, we're going to get rid of all the variables and write them in terms of trig trig functions, either sine, cosine, secant, cosecant, so on and so forth. Okay, so here is the rules on your notes. So looking for, in the first box, trigonometric substitution. It says right there for integrals involving the square root of a squared minus u squared, we're going to let u be equal to sine of theta. Now that's just kind of like the standard thing that you're going to have to memorize, but what I'm going to do from there is a couple different things. First of all, I can look at this and say, well, if I have u equal to a sine theta, how I could write that is u over a equal to sine of theta. Now I kind of tend to like, I'm a visual learner, so I'm going to kind of tend to go towards this triangular method here to remember things. If I think of my theta over here in this right triangle, and I know that sine is u over a, that is opposite of theta over hypotenuse, my third side is going to be the square root of a squared minus u squared. Okay, so if I look at that, and you really can't see that, so let me see if I can write that again. That would be the square root, using Pythagorean theorem, a squared minus u squared. Okay, which is what we have there. Now what I want you to think about is how can you write that square root as like a fraction where you have the radical over a constant, or with respect to theta. So with respect to theta, I would say, well, cosine of theta, wouldn't that be the adjacent, which is that radical, which is my a squared minus u squared, over my hypotenuse, which is a constant. So I'm trying to get a radical over a constant, so I'm looking at that saying, oh, well, I would use cosine. And then I get the radical by itself, so a times cosine theta would be the square root of a squared minus u squared. So in my integral, wherever I have an a squared minus u squared, where a is a constant and u would be any variables that you might have, I would substitute in a cosine theta for that. And then it's going to make it easier for me to find that integral. Now, another method that you can use is I can look at this and say, well, I let u be equal to, let me put down here method number 2. I let u be equal to my a sine of theta. Well, if I go back to my square root here and just substitute in for my u, my a sine of theta, and then I'm going to square both of those terms, we all see that I would end up with a squared minus a squared sine squared theta. So you can think of it more in terms of using trig identities as well. So you see that, and I'd have factor out an a squared, and I get a 1 minus sine squared. Well, what is 1 minus sine squared? I heard you all yelling that. Cosine squared, right? So if I have an a squared times cosine squared inside my radical, I would just get my a cosine theta. Okay? So again, you see I get the same result, just thinking about it a different way. Okay? But the main thing to remember in this first one, that if you have your a squared minus u squared underneath that radical, you're going to let u be equal to a sine of theta. Okay, then for number 2, for integrals involving the square root of a squared plus u squared, we're going to let u be equal to the a tangent of theta. I'm going to think of this as u over a equal to tangent of theta. So here's my theta. Tangent is opposite over adjacent. So I put those in my diagram, so therefore the hypotenuse of this little right triangle is going to be the square root of a squared plus u squared. So again, I look at my theta and think, how can I get that radical over a constant, where a constant is a and my variables are u, I would look at that and say, well, that would have to be using secant. Then the secant of theta would be my radical square root of a squared plus u squared divided by my a. So then I would multiply and I would have a times secant of theta equal to that square root of a squared plus u squared. Now I do have some restrictions for theta. Theta would have to be in this case between negative pi over 2 and pi over 2. These restrictions would be the same that we have like for arcsine, arctan, arcsecant. This first one up here, I didn't put any restrictions up here on this one. I would have theta, for this right here, theta would have to be between pi over 2 and negative pi over 2. And pi over 2. I think we can be equal to on those as well. Okay, and then we go to the number 3 down here. Let me get this all ready. So for this third one, if we have integrals involving u squared minus a squared, we're going to let u be equal to a secant of theta. Therefore, if I want to kind of look at my triangle, I would have u over a equal to secant of theta. Let's put in a theta right there. Secant would be my hypotenuse over my adjacent. So my third side is going to be my u squared minus a squared. So if I'm trying to rewrite this as a square root over a constant, I would be thinking, well, I would have to be using tangent. So actually, I would be using a times tangent of theta if u is greater than a, and theta would be between pi over 2 and 0. And I would have the opposite of a tangent of theta if u is less than negative a. And here theta would be between pi over 2 and pi. Okay, this is one that's not used as much, number 3. Okay, so let's go on and get started with some examples. First one, example 1. I have the integral of dx over x squared times the square root of 9 minus x squared. Okay, so I'm looking at this and I see that I have a squared minus u squared. Basically, I'm thinking I have u equal to a sine of theta. So in this particular example, I'm going to let my u, which is my x in this case, a is going to be my 3 sine of theta. So when I think about my triangle, I'm thinking x over 3 equal to sine of theta. So before I do that, though, let me kind of go back. Let me kind of put that over to the side. I'm going to have my x over 3 equal to sine of theta. Let's put that over there. And I need to figure out what is dx, the derivative of x with respect to theta. I'm going to get my 3 cosine theta d theta. Okay, now let's think about my triangle. Kind of sketch something in here. Put my theta down here. That's sine, so I have my opposite over my hypotenuse. So my other side is the square root of 9 minus x squared. And again, I'm trying to think, I need to get rid of my radical, so I need a radical over a constant. So I'm going to be using cosine theta is going to be equal to my square root of 9 minus x squared all over 3. Or basically my 3 cosine theta is equal to the square root of 9 minus x squared. Okay. Now again, if you're a good memorizer, there you go. You can memorize those and have them done really quick. Okay, so now we're going to substitute in. Wherever I see dx, I'm going to plug in my 3 cosine theta d theta. Wherever I see an x squared, I'm going to substitute in my 9 sine squared. And wherever I see my radical 9 minus x squared, I'm substituting in my 3 cosine theta. Okay, but unfortunately I have to extend my page and I'm not going to be able to see it. So going back and changing this, I have the integral of my 3 cosine theta d theta, that's my dx. Let me make sure I got that right. Yep. And then divided by my x squared, that's going to be my 9 sine squared theta. Then I need to substitute in for my square root of 9 minus x squared. Well, we said that's going to be the same as my 3 cosine theta. Now look at that. Isn't that so much easier? Well, it will be in a minute, okay? Doesn't quite look so nice right now. If I look at this, let's simplify as much as we can. The cosines are going to cancel. I have a 3 in the numerator. That's going to cancel out that 3. So I'm going to bring out my 1/9 out front. And then I get my 1 over sine squared theta d theta. Well, I'm going to change that a little bit more. Let's change that to the integral of 1/9 times the integral of cosecant squared. I'm sure we all remember what the integral of cosecant squared is. So you're thinking, what gives you a derivative that's cosecant squared? And that's going to be negative cotangent. So I have negative 1/9 cotangent theta plus c. And we're not done yet because we have to rewrite it back in terms of my x. So this is where my triangle comes into play again. I go back to my triangle, and what can I substitute in for cotangent of theta? So going back to that triangle, cotangent is going to be adjacent over opposite. So I'm going to get my square root of 9 minus x squared divided by x, and don't forget your plus c. Now we are done. Okay. So that's how we use trig substitution to make, or to be able to work this particular problem, make it a little bit easier to work, believe it or not. Okay, so I just want to give you just a slightly different method for number 1, just in case you are maybe wanting just to use your identities and kind of work the problem that way. That's fine. Kind of going back to the beginning where I have dx all over x squared times the square root of 9 minus x squared. Again, remember we're letting x be equal to 3 sine of theta. What you can do is just substitute that in right away. Again, we have to have our dx here, our dx, which is our 3 cosine theta d theta. If I substitute that in right away, I get my 3 cosine theta d theta. There's my dx. My x squared is my 9 cosine squared. Whoops, did the wrong one. 1 second. Squaring my x, I go to 9 sine squared x. And then my square root is my 9 minus my x squared. So that would be my 9 sine squared theta again. You can substitute your x in for everything like that. And then, as you can see, it's very similar to what I had before. I'm going to have my integral of 3 cosine theta d theta. I'm still going to have my 9 sine squared theta. Inside this radical, they both have a 9. I'm going to factor out front, and I get a 1 minus sine squared theta. So we know that we're going to be changing that 1 minus sine squared to cosine squared. So really what I have then is my integral of 3 cosine theta d theta. I still have my 9 sine squared theta. And then I'm going to have my square root of 9, which is 3. And then I have my 1 minus sine squared, which is cosine squared, and the square root of that is going to be cosine theta. So do we have that same statement in the previous method? Yeah, right there. So as you can see, we get the same result, just a little bit different. And I don't really care how you solve the problems. So I'll say see above. So if you don't like drawing your triangle or anything like that, that's fine. As long as you can get the same answer, you're good. Okay, so let's go on to example number 2. And again, if you prefer to do your problems doing a different method, that's fine. I'll be drawing my little triangle. So I have dx for number 2 all over the square root of 4x squared plus 1. Okay, so I'm looking at this and I have a u squared plus a squared. So I'm thinking I'm going to let u be equal to a tangent of theta. That's what my brain is thinking. So I'm looking at what is my u in this case. U is going to be my 2x. That's equal to my a, which is in this case 1 tangent of theta. So again, I'm thinking of this as 2x over 1 equal to tangent of theta, and I'm going to draw my little right triangle. And I also need to find my derivative. So on the left side, I get a 2 dx. On the right side, I get the derivative tangent. We all remember is secant squared theta d theta. So I do need to get dx by itself. That's going to be a 1/2 secant squared theta d theta to be able to substitute that in. Okay, looking at my triangle, my theta I'm going to put right here in the left-hand corner. Tangent is 2x over 1. So the hypotenuse is going to be the square root of my 4x squared plus 1. So again, I'm thinking I need to be able to substitute in for my radical, so I need a radical over a constant. So looking at that triangle, it's going to have to be secant. Secant of theta is going to be my radical for x squared plus 1 over 1, but again, we don't need that. Okay, so let's substitute in. Let me switch colors here since we're substituting in. Let's go purple. My dx was in the numerator. So in the numerator, I'm putting my 1/2 secant squared theta d theta. My denominator, I had my square root, which we all know now is square root of, whoops, I'm getting rid of that. I don't want that square root anymore. We're substituting in for that square root of 4x squared plus 1, and we're going to be plugging in secant theta. That's why I did not need all that long line. Okay, so let's clean this up a little bit. What I really have, bring the 1/2 out front, and secant squared over secant, I just have a secant theta d theta. So what is the integral of secant? 1/2 is tagging along. Do you remember that one? It's the natural log of the absolute value of secant theta plus tangent theta. We probably haven't seen that one for a while. Don't forget to add your plus c. And remember, we cannot stop there. We have to write it back in terms of x. So secant theta is my square root of my 4x squared plus 1. Tangent theta, I go back, and tangent theta was 2x plus c. And that is my answer. Okay, so example number 3. So if I'm looking at example number 3, that's a little bit different because I have a radical there raised to a power. So if I have to the 3/2 power, let's write that down. I have x squared plus 1 to the 3/2 power. I'm going to think about that if I want to use trig substitution as the square root of x squared plus 1, and then that quantity cubed. Okay, now what I'd like for you to do is have somebody pause this presentation so that you can try number 3 and number 4 on your own. And then when you, the majority of the people are done, let somebody know so you can turn the video back on. So go ahead and put the video on pause so everybody can try example 3 and example 4 on your own. Okay, so just wanting to run through these real quickly since you probably already have them done. Just wanted to double check. On example 3, did you let u be equal to 1 or a tangent theta, which would be x equal to 1 tangent theta? So you would set secant theta equal to your x squared plus 1, that's in the radical. Okay, and then I would have substituting in everything. I had the integral of secant squared theta d theta all over secant cubed theta. And then simplifying that, I just get 1 over secant, which we all know is the integral of cosine. The integral of cosine is sine of theta, but remember you cannot stop there. You have to finish it out and write it back in terms of x. So we get this x over the square root of x squared plus 1 plus c. And you go back to your triangle to figure out what is sine of theta. So using that triangle once again, kind of helpful there. So that's my final answer for number 3. Make sure there's no mistakes. I'm sure you'll let me know if there was any. Okay, and then example 4, I had the square root of 1 over the square root of 25 minus x squared dx, so I'm going to let u be equal to a sine of theta. That's what I'm thinking of. So x is equal to 5 sine of theta. So x over 5, if you're making your triangle, is going to be equal to sine of theta. So there's all my preliminary work on that. Dx would be 5 cosine d theta. So setting up my triangle, I get 5 cosine theta equal to that square root of 25 minus x squared. That's what I'm going to substitute in for that radical in my problem. So get rid of this. Substituting in to my original, my numerator was just 1 dx. So my dx was my 5 cosine theta d theta. My denominator is just my radical, so that's my 5 cosine theta. Well, if you notice, all I get is the integral of 1 d theta. Well, the integral of 1 is theta. And then you have to go back to the triangle once again. How do I solve for theta? Well, that's theta could be, there's lots of probably different ways that you can write that. I wrote mine as arc sine of x over 5 plus c. Because I look back at, to write it in terms of x, I went back to this. Okay, I guess more like this one. So if I wanted to solve for theta, I would just take the arc sine of x over 5. There's my answer for number 4. Okay. Okay, last example, example 5. This one just looks very strange. Okay, so I have this 4 plus 4x squared plus x to the fourth, and there's no radicals. Well, this is a lesson in trig substitution, so I want to try and see, can I get this written in terms of a radical? So I'm going to spend a little bit of time here just doing that. That denominator, does it look like it can factor? Most likely, yes. So I get a 2 plus x squared quantity squared. There's my dx. Well, how do I write that as a radical? Well, if I want to write that as a radical, I'm going to think of this as 1 over the square root of 2 plus x squared. And now, guess what? What power is that going to be? It's going to be to the 4th power. Okay, there we go. Don't forget the dx there. So yes, I can take this and factor it. It's a binomial squared, but then throw in that radical and it's going to be raised to the 4th power. Now I'm ready to do some trig substitution. I see that I have a 2 plus x squared. That's like an a squared plus u squared. So I'm thinking, my brain is thinking, that I'm going to be using something like u is equal to a tangent of theta. So in this case, u is just my x. My a is my root 2 tangent of theta. Again, I'm going to draw my little triangle, so I'm going to write tangent of theta equal to x over root 2. I also want to take the derivative of the x. So the derivative of tangent is secant squared. So I have dx is my root 2 secant squared theta d theta. I'm going to draw my little triangle, so I have all my parts here, then I'll be ready to do some substitution. Here's my theta. Tangent is my x over my root 2. So my hypotenuse is going to be x squared plus that root 2 squared, so x squared plus 2 inside that radical. So I'm trying to get a radical over a constant, so I'm going to be using secant. So I'm going to have secant theta equal to my square root of x squared plus 2 all over root 2. So basically for that radical, that x squared plus 2, I'm going to be substituting in root 2 secant theta. Okay, I think I'm ready to do my substitution. Are you with me? Okay, here we go. Where am I at? My dx, I'm going to put that in my numerator. So my dx was my root 2 secant squared theta d theta. In my denominator, remember I had that square root of 2 plus x squared to the 4th power. So that radical is now going to be, substituting in for that radical, I'm going to get root 2 secant theta. And now that is raised to the 4th power. Okay, that doesn't look bad. So I have the integral of root 2 secant squared theta d theta. In the denominator, making that look a little bit nicer, I'm going to have root 2 to the 4th power is just going to be 4, and then I'm going to have secant to the 4th theta. Well, I'm going to simplify that down a little bit. I'm going to bring my root 2 over 4 out front, and then I have 1 over secant squared theta, d theta. Then I'm going to change that a little bit more. Secant squared theta in the denominator, that's really 1 over secant squared is cosine squared theta. Okay, now, here is where we had, I think, a problem the other day. And in our notes, in a box somewhere, I think when we were doing, gosh, in the last lesson or two, I wrote down a little note to you to see if you remember. We'll put it here again. Power reducing rules. Cosine squared theta, do you remember what you can rewrite that as? That is 1 plus cosine 2 theta divided by 2. If it's sine squared, it's very similar. It's just 1 minus cosine 2 theta. But yes, we're going to use that right there. Okay. Substituting in that power reducing, I'm going to get, still carrying along my root 2 over 4 integral. I'm going to bring this 1/2 out front, and then I get my 1 plus cosine 2 theta. D theta. Can't remember that. Can't forget that. So this 1/2 that's hanging around here, I'm going to bring it out front and multiply it times that root 2 over 4. So I get my root 2 over 8 integral 1 plus cosine of 2 theta d theta. There we go. Now we're ready to do this. So that root 2 over 8 is carrying along. And then the integral of 1 is theta. I have to integrate cosine of 2 theta. Your brain needs to think, oh, I don't want to use u here, do I? Maybe I'll use w. W is equal to 2 theta, so dw is equal to 2 d theta. And right there, I'm just looking at this part right here. I'm integrating this part right here. I don't have a 2 d theta, so I need to bring a 1/2 in front of that. So I have plus a 1/2 of my sine 2 theta. Okay. I'm thinking about if I were to split up this integral, so I'd integrate 1, this is what my brain's thinking, integrate 1 d theta plus integrate cosine 2 theta d theta. And I was just kind of doing mentally my, or just real quick, my u substitution or my w substitution for that second part to that. Okay, I did do an integral. I can't forget my plus c. And then, you know, I can leave that sine of 2 theta there, but I know I need to get rid of that theta and rewrite it in terms of x. So do you all remember how we rewrite sine of 2 theta? Oh wow, this is like the problem that never ends. All trig review, love it. Sine of 2 theta, you could probably shout it out at me right now. 2 sine theta cosine theta. Oh yes, we will all remember that. So then I can see that these 2's are going to cancel. So now this will be easier for me to substitute in for theta now and get rid of, substitute in, not really for theta, but for my trig, like my sine theta, my trig functions. So I get my root 2 over 8. And then theta, wow, let's go back. What in the world is theta going to be? Looking right here. If x over root 2 is equal to tangent of theta, theta is going to be arctan. Arctan of x over root 2 plus, then I have the sine of theta. Look back at that triangle. I'm not going to scroll back. Look back at that triangle. I get x over square root of x squared plus 2 times a cosine, which is root 2 all over the square root of x squared plus 2 plus c. Wow, that really looks ugly. Let's clean it up just a little bit more. I get my root 2 over 8 out front. My arctan of x over root 2 looks good. And then that last part, I can multiply those two fractions together and get plus x root 2. My denominator is just my x squared plus 2 plus c. That is my answer. Boy, that was fun. I'm sure you enjoyed it as much as I did. Okay, so you have some homework to do. And that's my end of my lesson on trig substitution. Remember, you use this as a last resort. And I call this integration by desperation because we don't want to use this as a first choice. Thank you very much, and we will see you later.